Good afternoon, everyone. I'm Mukunda Pudasaini. In today's presentation, I'm going to talk about prediction of radiobiological outcomes in radiotherapy of lung cancer through an artificial neural network. The purpose of our study is to develop an artificial neural network to predict radiobiological parameters in radiation therapy for lung cancer patients. Let's talk about the motivation behind our study. Lung cancer has been the leading cause of cancer death in the world. According to Cancer Statistics 2019, the estimated death cases were 142,670 only from lung and bronchus in the United States of America. National Cancer Institute data show that the 5-year survival rate for lung cancer is only about 18.6%. With the development of the new technologies, there was seen improvement in the overall cancer survival rate, but the improvement rate for the case of lung cancer is still very low. This is the outline of my presentation. Let's move to the introduction. The goal of radiation therapy is to deliver the prescribed dose to the tumor volume while minimizing the dose to the adjoining normal tissues. The treatment plans are evaluated by the dose and dose volume criteria with the assumption that the dose volume criteria correlates with the radiobiological outcomes. It has been widely accepted that the treatment plans should be evaluated based on the radiobiological responses rather than the dose volume criteria. There are several mathematical models like the cited here that are used to estimate the radiobiological parameters, but those are using advanced algorithms and many tissue-specific parameters. It could be very useful if we can develop an simple neural network that can calculate or predict the radiobiological parameters without using those advanced algorithms and tissue-specific parameters. In this section, I'll talk about the patient data selection, TCP and NTCP calculation, and neural network model. In this retrospective research, we have chosen 100 random lung cancer anonymized patient treatment plans from 21st Century Oncology, Boca Raton, Florida. Those all treatment plans we have selected were approved by the radiation oncologist and were delivered to the patients from January 2016 to September 2019. Our calculation of the tumor control probability and normal tissue probability is based on the dose volume histogram. Equivalent uniform dose-based linear quadratic model was used to calculate TCP and NTCP. This is the demographics of the treatment plan of the patients. Here, in this table, the PTV represents the planning target volume. The range of that we found in the 100 patients is from 2.7 centimeter cube to 881.8 centimeter cube. The age of the patients were from 44 years to 95 years. And the total dose delivered to the patients were ranging from 3,500 centigrade to the 6,000 centigrade. And the total dose given to one patient was varying in the fractions from 4 to 28. The hotspot dose is the maximum dose that the tumor receives during the treatment relative to the prescribed dose, and it was measured in percentage relative to the prescribed dose, which is ranging from 104.1% to 126.2%. This is a typical example of DBS from one of our patient cases. This shows the relation of the radiation dose to the structure volumes. It is the commonly used evaluation tool to compare the doses with the other treatment plans or with other structures. Here the PTV is the planning target volume that is receiving the maximum dose within like whole volume of it. That's the purpose of the treatment actually. And the other structures with lower doses on the left side, those all curves are the normal organs receiving some dose. The green is esophagus, the brown is airway, red is spinal cord, the orange is the right lung, and the pink one is the left lung. To calculate TCP and NTCP, we have to know the equivalent uniform dose, which is defined by this equation. Here, in the UD equation, the VI is the partial volume, ith partial volume receiving dose DI in gray, and alpha is a unitless parameter that describes the volumetric relationship of the dose response relationship. These equations are used to calculate TCP and NTCP. Here, the normal tissue complication probability first equation has the quantity equivalent uniform dose, and TD50 is the tolerance dose for the 50% complication rate at a specific time interval. We have used 5 years in the Imami et al. Normal tissue tolerance. And gamma 50 is the slope of the dose response curve. The second equation, tumor control probability, uses the similar equivalent uniform dose, and the TCD50 is the tumor dose to control 50% of the tumor when the tumor is homogeneously radiated. The total dose delivered to patients are given in different fractions per different dose per fractions. So to make the consistency to all the treatment plans, we have to convert them into biological equivalent dose of 2 gray per fraction, which is done by using the equation. Here, n is the number of fractions given for the total dose. D by n is the dose given per fraction. Alpha beta ratio is the tissue specific linear quadratic parameter of the irradiated structure, and D is the total dose of the treatment course. The NTCP and TCP calculations were performed using freely available MATLAB program, eudmodel.yam, provided in the paper Guy et al. 2007. These are the tissue-specific parameters for TCP and NTCP calculations. Here, alpha, gamma 50, alpha beta ratio for PTB and other normal structures are shown. TCD50 is the tumor control dose for 50% control of tumor for the target for the tumor, and TD50 is for the dose for 50% complication for the normal organs. Let's move to the artificial neural network. Artificial neural networks are the statistical models with mathematical structures within to mimic the learning dynamics of the brain. ANNs have 3 layers which are made up of logical units, and they are connected with one another by the weights. The 3 layers of logical units are input layer, hidden layer, and output layer. The input layer feeds the information, while nodes in the hidden and output layers process the information. In this picture, we have chosen a typical example of ANN with 3 nodes in the input layer, 2 nodes on the output layer, and 4 nodes in the hidden layer. In our study, this table represents the inputs and outputs we have selected. The inputs we have chosen are the prescription dose, a number of fractions in which the dose is delivered, planning target volume, and how many fields were set up to provide the dose, and then the maximum dose delivered to the tumor, and mean doses to the normal tissues like esophagus, spinal cord, heart, and contralateral lung. And treatment modality, there are several modalities, and also the location of the tumor in the lung. The outputs are, target outputs are our calculated values of TCP and NTCPs, as we discussed earlier. For the data preparation, our data is ranging from very high value to very low value. The NTCPs obtained sometimes were in the order of 10 to the power minus 13, and the total delivered dose was going up to like 6,000 centigrade. So to make the consistency in the input and output, we normalize all the continuous input output data in the range 0 to 1. And our non-numeric data, treatment modality, we have 3 different modalities: stereotactic body radiation therapy called SBRT, volumetric modulated arc therapy called VMAT, and intensity modulated radiation therapy called IMRT. So those for modalities we divided into sub-input categories and assign them value 100, 010, and 001. Similarly, we divided the location of the tumor in the lung into 4 different parts: left lower lung, left upper lung, right lower lung, and right upper lung, and assigned and divided them into 4 subunits with the values 1000 for left lower, 0100 left upper, 0010 right upper, and 0001 for right lower. To train and test the validity of the neural network, we have used the MATLAB 2019 input-output curve fitting app to train and test the input-output pairs. We use scale conjugate gradient backpropagation algorithm with 1 hidden layer that has 16 nodes that is fitted with our 11 inputs and 5 outputs parameters. The available data were employed 70% for training and 30% for validation and testing. The fitting error was observed by mean square error with the regression values. Lower the mean square error values means the better is the performance of the network. Let's move to the results. At first, I will talk about the TCP and NTCP results. Then I'll go to the neural network results. The diagram, light blue diagram in the left is the TCP calculated from the EUD model for all 100 patients here. We can see that the TCP is varying from 17 to 100%. The variation, the smaller TCPs indicate that the treatment plan was palliative rather than curative. But for the curative treatment plans, the TCP were near 100% value. Most of the cases that were above 90% cases. On the right side, the orange diagram is the same TCP plotted in the logarithmic scale for a different view. Here, the orange one is for NTCP plotted for spinal cord, and on the deep dark blue, the plot is negative logarithmic of NTCP of heart. Here, if we plot like without logarithmic scale, then we won't see the differences in their values. The 0 values in some cases, some patient cases, we see on the graph is because for that patient cases, either the normal organ is not exposed to the radiation, or the dose is not measured for that specific organ. Similarly, here the green is NTCP for esophagus, plotted in the negative logarithmic scale of the NTCP, and this blue is for NTCP for contralateral lung. Let's move to the regression fitting of the neural network. From this is the fitting, regression fitting of the neural network for our all 100 patient cases, 70% for training. So we got the R value for training 0.97, the R value for validation 0.85, and R value for testing is 0.96. The overall for all 100 cases, the R value is found 0.94, which is close to 1. This means R equals 1 implies the ideal relationship, while the R is equal to 0 implies random relationship. This is the performance of neural network. We saw the mean square error decreasing every next epoch until the 48th epoch was observed for the validation. And best performance was observed when MSE value was 0.0071 at the 48th epoch. The error histogram for the network performance is presented here. The orange central line that represents the zero error. So we see that on many instances, the error is closer to zero. But in some cases, the error is little more, which indicates the good performance of the neural network. This is our preliminary study. We are still studying this project. Preliminary results of this study show that we can develop a neural network that can predict the radiobiological outcomes without using those advanced algorithms and those tissue-specific parameters. So we can produce radiobiological indices if we have a pre-trained neural network or previous data, and if we have input parameters available. As we see, the overall regression value is closer to 1, that's 0.94. The model is predicting radiobiological outcomes with promising result. For the full performance validation of our neural network, in the case of lung cancer patient, our work is in progress still. We are currently working on to find the correlation of the dosimetric indices like homogeneity index and conformity index with the radiobiological indices. And we are also studying the optimization of the doses to tumor and normal tissues by developing a personalized treatment plan using supervised learning. I'd like to thank 21st Century Oncology, Boca Raton, Florida, for providing research opportunity at the clinic and providing such a nice environment to learn so many things. I acknowledge especially Mike McDonnell, the dosimetrist at 21st Century Oncology, Boca Raton, Florida, for teaching me treatment planning process. Thank you. I'll be happy to answer your questions if you have any.